Hello. Today we're going to be looking at inter-rater reliability, specifically inter-rater reliability for categorical data, that is, situations in which we are placing observations within given categories. A separate video will cover the subject of inter-rater reliability for dimensional ratings. So here we go. We're going to look at a few slides together and see how this works out. So again, this is a straightforward how-to guide. We're not going into the theory here. That will happen in separate presentations. So categorical judgments, what do I mean by that? Essentially, we're talking about a nominal scale, something where the question isn't how much of that is there, but rather which kind of thing is it? In other words, the possibilities are qualitatively different than one another. So we aren't really quantifying, rather we are, well, categorizing, for want of a better word. So, there are many examples of where this happens, male versus female, different diagnostic categories, such as the distinction between a schizophrenic spectrum disorder and a mood disorder, animal identification, is that a house finch or a purple finch, et cetera, et cetera. Clearly, for many of us, the diagnostic problems are the ones that we are most frequently confronted with in terms of having to actually study how reliably we are able to make these calls. I want to add here that I'm going to be using just examples where there are just two possible categories. All of the same principles apply if you have 3, 4, 5, 6 or more categories. But of course, calculating things starts to get a bit more complicated, more cumbersome. So let's just start with the basics. Okay, so how do we establish how reliable these judgments are? And remember, reliability here is essentially synonymous with objectivity. To what extent do independent observers arrive at the same conclusions about what it is that they're witnessing? Well, we have to begin at the beginning with percentage agreement. Now, that's not actually going to be good enough for serious purposes, but it's where we have to begin. All the percentage agreement means is, how often do the judges or raters agree with each other relative to the number of cases that they've examined independently? So if you and I are the two judges and we both say, yep, that's one of them, we've agreed. If we both say, nope, that's not one of them, we've agreed. The disagreements, of course, would be those cases in which either one of us has said yay, but the other has said nay. Now, typically, we're going to represent this using a contingency table. And for dichotomous judgments, that's going to be a 2x2 contingency table. And here's an illustration of what one would look like. So you have the two rows, which would be yes or no judgments, or schizophrenia or depression judgments or whatever, made by one of the raters. The two columns, column 1, column 2, would be the similar judgments made by the other rater. And of course, we could then add up the totals for all the yeses from both, all the nos from both, et cetera. That's it. So the formula is here. We're going to walk through what goes into it. Back in the contingency table, cells A and D are the ones that reflect agreement. If we both say yes, or if we both say it's a house finch, it goes into, those are counted in cell A. If we both say nay, it's not schizophrenia or it's not a house finch, it goes into box D, whereas cells B and C are the ones that capture the cases where we disagree, where I said yes and you said no, or you said yes and I said no. So agreement is quite simply, the number of cases where we agreed, the sum of cells A and D, divided by the sum of all the times that we've done it, that we made an attempt at identifying what it is that we're looking at. That's actually it. So I'm going to use a make-believe example here. And I'm using a somewhat fanciful example in the world of psychodiagnosis. Not entirely fanciful, but a little bit so. So we're running a counseling service, and we realize through bitter experience that those patients who come to us who suffer from psychotic disorders, things in the schizophrenia spectrum, for example, have different treatment needs than do their non-psychotic peers. And we want to learn to recognize this early in the game before we've invested in pointless treatment for people who it's not going to benefit. So we have Dr. Schnitzel on staff, and Dr. Schnitzel proposes that we will use human figure drawings for this purpose. We'll have each new client draw a picture of a person, and that these drawings should be identifiably different than those if they're done by someone with a psychotic disorder, as opposed to if they're made by someone with a non-psychotic problem. Dr. Schnitzel's colleague, Dr. Martinez, says that's a good idea, but really we ought to establish whether we're on the same page here first. So if we're going to be the two people looking at evaluating these drawings, we're not always both going to look at every individual patient. So, are we being objective here? Are we arriving at similar conclusions? So Dr. Schnitzel, of course, agrees, and the two psychologists collect 100 of these drawings by clinic clients and independently rate each of the drawings. By the way, the independent piece here is important. If they talk about it with one another, it's pretty easy to arrive at an agreement that way. It doesn't mean that you're being objective, it just means you're being persuasive. So here's the story. You have two judges, Schnitzel and Martinez. You have a sample of 100 cases where they've looked at this particular little test protocol, and here's what we get for results. So, well, first off, they have to look at all these drawings, which, are quite variable naturally, and for each one, they're making a simple qualitative judgment call: psychotic, not psychotic. And again, here's the results. So in cell A, we see those cases where both Dr. Schnitzel and Dr. Martinez have said that the patient is psychotic. In cell D, down here, we see those cases for whom both Dr. Schnitzel and Dr. Martinez have said they are not psychotic. That's cell A and cell D, respectively. Then in cells B and C, we see those cases for which one has said psychotic and one has said not psychotic. So in cell B, it's, Schnitzel said psychotic, Martinez said not. In cell C, Martinez said psychotic, Schnitzel said not. So if you add across the different rows and columns, you find, that each of them has actually identified 40 cases as probably psychotic and 60 as probably not. It doesn't have to work out evenly that way, by the way. It often won't. And we have a total, again, of 100 cases. So there's our contingency table. Now, how closely did they agree? Well, if all we're doing is looking at percentage agreement, well, we know they agreed that 30 cases were made by people with psychotic disorders, and they agreed that 50 of the drawings were made by people who were not psychotic. So and of course, they disagreed on the remaining 20 cases. So the calculation, is A plus D would be 30 plus 50, divided by, of course, the 100, which is the total number of cases rated. And that gives us a value of 0.80, or if you wish to represent it as a percentage, you'd say 80%. They've agreed 80% of the time. And their conclusion is that their procedure is actually a reasonably reliable one. Now, is it? Well, maybe and maybe not, you see. And here's where I have to get a wee bit technical and get our heads around the way in which this falls short. Not that 80% is either good or bad. I'm not even addressing specifically that. What I'm saying is that whatever number you get here, you don't know whether it's good or bad. Well, I guess some numbers are obviously bad, but for the most part, you just don't know. So why not? What's wrong with percentage agreement? It's so intuitive, it's so simple. The problem is that sometimes we're going to agree randomly. Sometimes the two people will just arrive at the same conclusion, not because they're judging things similarly, but just because that's what randomness does, especially when you only have two possibilities here. And so what this means is that how good a certain percentage is, 80% or 90% or 70%, whatever it is, how good that is depends on the base rate of actual cases. So here we were concerned with identifying cases that fell into the category of psychotic. Well, how many of the clients at our clinic actually do fall into that category? Now, if the ratio here is pretty close to 50-50, honestly, percentage agreement would work fine. But we don't use percentage agreement because it's rarely going to be 50-50, and you never know that it is just because somebody says we agreed 80% of the time. Think about it. If it's 50-50, we're going to agree randomly about 50% of the time. But the further you deviate from that, the less likely, how should I put this? The more likely it is that you're going to agree by chance, basically, if your guesswork follows the base rate information. So again, we need to know what proportion of the clinic's clients actually suffer from psychotic disorders in order to be able to evaluate that percentage. Now, as you'll see, there's a kind of a workaround here that helps us in this case. So let me give you a few examples here. So we're trying to diagnose schizophrenia or psychotic disorders more broadly based on this simple test. And we're agreeing 80% of the time. Well, if it was a base rate of 50%, then we would be expected randomly to agree about 50% of the time. That is, half the time I say psychotic, and in half of those cases, you also say psychotic. That's 25% of cases in which we agree that it's a yes. And half the time I say no, and in half of those cases, you also say no, which is 25%, 0.5 times 0.5, 0.25, that we're agreeing. So 80% looks pretty good. It's a lot higher than 50%, right? It's way better than random. But now, suppose the base rate is 20%, or 80%, by the way, but say 20%. Only 1 in 5 of our clients is psychotic. Well, now, there's 1 in 5, 0.2 cases where I say psychotic. There's also 1 in 5, 0.2 cases where you say psychotic. If you cross multiply those, 0.2 times 0.2 is 0.04. We're agreeing 4% of the time about presence of psychosis, but 80% of the time I'm saying no, and 80% of the time you're saying no. 0.8 times 0.8 is 0.64. So 64% of the time we're agreeing that it's not a case of psychosis. You add those together, and in fact, we would expect through random guesswork alone that we would be agreeing 68% of the time. Now, 80 is greater than 68, but it's not much better, is it? So we're now feeling like, the diagnostic procedure is, maybe, it's better than nothing, but it's not great. And it only gets worse. I'll give you just one more example, but the more extreme this becomes, the worse it's going to get. So what if the base rate is just 10%, or of course it was 90%? Well, we're only going to agree on the yeses in about 1 out of 100 cases, 0.1 times 0.1. But we're going to agree on the no's 81% of the time randomly, because 0.9 proportionately, 0.9 or 90% of the time, I say no. And 0.9% of the time, you say no. And again, if you just randomly cross multiply, that's 0.81. So we're actually going to agree 82% of the time, which is basically how much Dr. Schnitzel and Dr. Martinez agreed. Let that sink in. This is where base rate information is very, very important. Now, here we don't know the actual base rate of psychotic disorders in the clinic. What we can work from, though, is the rate at which it is being diagnosed by our judges. So here's what we want to do. We want to correct for chance. The statistic most often used for this purpose is known as Cohen's kappa, or the kappa coefficient, introduced by Jacob Cohen 50 odd years ago. Now, I'm not going to make you hand calculate this, but I'm going to show you how to in case you ever need to. It's conceptually very important, though. So this is the equation. And in this equation, P sub O represents the observed level of agreement, the proportion of cases in which we've agreed. P sub E represents the agreement we would have expected based on chance. So I'm going to show you how it's done, though I'm also going to show you briefly an online calculator that can be used for this purpose. And in everyday practice, why not go ahead and use the online calculator and reduce the risk of arithmetic errors, right? So calculating Cohen's kappa. The first thing you do is actually calculate observed agreement. That's just the percentage agreement. So that's what we already have learned how to do. All the cases where we agreed, cells A and D, divided by the total number of judgments made. Then we need to calculate what would be expected based on chance. And the technical way of doing this is what's shown here. Instead of writing A plus B plus C plus D out multiple times, I'm just going to use the uppercase N to represent that value. So you take all the times judge number one, say, I forget which one, say Dr. Martinez said yes, and divide that by the total number of judgments made. Multiply that times the same value for the other judge, Dr. Schnitzel. So, how many times did he say or she say psychotic divided by the 100? How many times did she or he say psychotic divided by the 100? Multiply those. And then you do the same thing for the situations where each judge has said no. So you would add together cells C and D, divide by the total number of judgments. You would add together cells B and D, divide by the total number of judgments, and multiply those two figures. And then you just add what you got in those last two lines to get PE. You see it's not hard, but it's a bit tedious, right? You don't want to have to do this a million times a day. But once you have these two figures, you just insert them into the equation. So I'll show you one scenario where it's done. So observed agreement, as we know, was 0.80, right? 30 plus 50 divided by 100 was 0.80. Expected agreement, and this is a little more technical than the way I'd done it earlier, but this is how it's done for Cohen's kappa. I would take the 40 cases where one doctor said, yes, psychotic, divided by 100, the 40 cases where the other doctor said, yes, psychotic, divided by 100, and multiply those to get 0.16. And I would do the same thing for the 60 cases where each of them had said, no, not psychotic, to get 0.36. 0.6 times 0.6 is 0.36. I'd add those together. And the fact is that we would expect them to agree about 52% of the time by chance alone. So kappa is going to be equal to 0.8, the observed agreement, minus 0.52, the expected agreement, divided by 1 minus the expected agreement, 0.52. Just working through the arithmetic, that's 0.28 divided by 0.48, which gives us a value of about 0.58. So they're doing better than chance, certainly. Chance would have predicted only, 52% agreement. They've achieved 80%. And Cohen's kappa is a way of representing how much improvement we are seeing over chance. So, how'd they do? What does that mean? Well, there's no mathematical rule that says this is the level of kappa you need. All we have really are conventions that the various researchers working in this sort of field have agreed on. And this is one of the more widely used sets of guidelines here. So where Dr. Martinez and Dr. Schnitzel are is towards the upper end of the range referred to as moderate agreement. In research contexts, that would actually not be bad. In clinical practice, it's not quite where you'd want it to be. Generally speaking, for example, if you look at the field trials for a new edition of the American Psychiatric Association's Diagnostic and Statistical Manual of Mental Diseases, they look for kappa values above 0.6. They want to see it in the substantial agreement range, and they really hope to get towards the upper end of that range. So Dr. Schnitzel, Dr. Martinez agreed moderately well, although it's debatable whether what they're doing is really ready for prime time, or that is ready to be used as part of the, as a major part, a mainstay of the clinical assessment process. Though, it may not be a bad thing to throw in there as a supplementary procedure. And could be that if they work together for a bit on this and get the rating scales more properly calibrated, they might well reach the level of substantial agreement. Though there still is a caveat here, as there is for, by the way, for the Diagnostic and Statistical Manual of Mental Disorders itself. This only speaks to the objectivity of the judgments. It does not speak to their validity. We have no way of knowing whether the people they're diagnosing one way or another really are suffering from specific disorders of that type. Again, that's not only true in my fictitious example here, it's true of the DSM itself. The question of the extent to which a diagnostic category even exists, let alone the question of whether we're doing a good job of diagnosing it, is logically separate from the question of whether we're able to achieve agreement. However, as you should know as students of assessment, being able to achieve agreement is a necessary first step along the way. Okay, so we are out of the slideshow, and I will stop sharing that. I did want to quickly show you give me a moment, one more thing here, which is a web page containing, where are we now? Containing, kappa. Well, that's frustrating as all heck. Huh. Okay, now that I've spoiled the whole presentation, this is a site that's linked to by the PowerPoint, by the way, at Vassar College runs a very nice statistical page. And here you can actually calculate Cohen's kappa at will. We would generally just go for the so-called unweighted kappa. Don't worry about the fancy stuff. In our situation, we would simply select two categories. Notice that now we have 4 cells lit up, so we could put in whatever numbers we wanted into those cells. Let's say we make a situation that's similar to, though not identical to, the one we've already looked at. So 30 yes, yeses, 50 no nos, and so forth and so on. And you just hit calculate. All the row and column totals appear, and kappa appears, and it's 0.5876. Again, this is very similar to, though not identical, to what we worked out by hand just before. So all that being said, I'm going to say good day. Sorry about the bobble at the very end there, and we'll see you next time for inter-rater reliability of dimensional ratings.